Greetings. So, this time we will learn about an extension of the bin packing problem, which is called the strip packing problem. Strip packing, in which we have an input, so a sequence of rectangles. We have a sequence of rectangles, so sigma I, the ith input, is just the width of the rectangle and the height of the rectangle. So the height and the width is always between 0 and 1. And this is like where you are just packing your objects onto in a mall onto the counter. So we want to pack these rectangles no rotating and no overlapping. Onto a strip and unit width strip, which is an infinite strip, so it's an infinite 1 times infinite rectangle, if you prefer, minimizing the total height we actually use from the strip itself. Now let's just see an example, because it's easier to understand the problem if you have examples for that. So if the input is a sequence of rectangles, say 0.4, 0 times 6, this means that the first rectangle has the width 0.4 and the height of 0.6, and then comes another rectangle 0.3, 0.3, and then comes the third one 0.5, 0.4, and then comes the 0.5, 0.7, and then comes 0.7, 0.1. I believe that's enough. Then one possible solution is the following. So what you do is you just take a unit width and possibly infinite height strip, and you just have to arrange these rectangles onto this strip. So for example, it's probably a good idea just to place this guy, because this is a narrow and quite high rectangle. It might be a good idea just to put this here somewhere. So the width of this guy is just 0.1. I will just write 1 instead of 0.0, and so on. And the height of this guy is 7. Okay, so we just packed this guy. And then we still have a total width of 0.9 left. And coincidentally, 0.4 plus 0.6 5 happens to be 0.9 as well. So it might be a good idea just to put the 0.4 width and 0.6 height, so that makes it 6 times 4 to put here, and just put next to this guy the shorter guy, which is 0.5, and it has a height of 0.4. Yeah, that's a possibility. And then there are only 2 rectangles left, and that's, for example, a possible solution that just to put here the box having height of 0.3 and also width 0.3, and then here we also have a height of 7, and this 0.7 times 0.1 won't fit here into the middle because the width here is 1 and the width here is 3, so you would only have 0.6 space there, but you can of course just put this 7 times 1 object here, which will make the total height used here is just 0.8. Remember, I didn't write out the 0.0.0 stuff, and of course you won't have to if you happen to have an exercise somewhere in the near future about this problem. So that's one possible solution, and actually this is optimal. Now in general, since again the total area which you have to use is exactly the sum of the areas of these rectangles, and the width of the strip is 1, it means that you have to use a height numerically being the same as the total area of these rectangles. So the optimum solution is at least the sum of the areas of these rectangles, which is of course wi times hi, so it's from 1 till n. And of course the optimum is again lower bounded by the maximum height, again since we had a rectangle of height 0.7, this makes the optimum to be at least 0.7, because you have to pack that rectangle as well. So this is quite similar, both of these guys are quite similar to the classical case of the beam packing problem. So actually beam packing is this, with of course and the I mean this was just the scheduling problems, lower bound of course. So beam packing is this with the hi being 1 for all the possible objects, because, well, for example, so if you have a standard beam packing with, say, objects, so let's just give the size of the objects like 0.6, 0.5, 0.3, 0.4, and I mean 0.1. Probably that was one of those inputs we already had. Then we can transform this into a strip packing problem of each object having a height exactly 1, 0.51, and so on, 0.31, and so on, 0.41, and 0.11. And that's quite, so I could say that it's equivalent, because if you just have bin packing of, say, let's just push the 0.6 here and the 0.4 there, like, okay, so that's one in the classical case, and then you are just pushing the 0.5 into one of those bins and the 0.3 as well and the 0.1, yeah, that fits still, so it's 0.9. So you can push all the objects, the original objects, into two bins. Then the same solution can be translated into a strip packing solution, because you are just using the height 1 and the width 0.6 here, yeah, with 0.1 times 10, yeah. And then this is the 0.4, but it's also having I think I'm just using these actual values in this case. And then you will have the second, which is 0.1 times 1, and then you will have the 0.3 times 1, and then you will have the 0.5 times 1, and you still have some space left, but here the value, the height is 2, and here again the number of bins is 2 as well. So this is what it means that the strip packing is a more general construction, because you can just convert the original one into an equivalent strip packing. It's quite easy to show that this if the first one had the optimal solution, then you can just transform it automatically to an optimal solution of the second one, and the other way around. So the optimum of the second one can only be, so there will be an optimum like this depicted, so you won't have any advantage of using both dimensions in this case. Now, okay, so for this problem, we of course, since it's a generalization, we have an algorithm. So an online algorithm for this problem, an online algorithm for strip packing is the so-called next fit shelf algorithm, which takes a parameter somewhere between 0 and 1. Okay, similar to the harmonic algorithm in the classical case, the harmonic algorithm takes the parameter k, how many bins should it construct, and the next fit shelf will just take a parameter r, which is in this case a real number. So an online algorithm goes as follows. This algorithm, so the NFS next fit shelf R creates, say, shelves in the strip and each shelf will have a height. A strip, these shelves will have the heights 1, which is actually r to the 0, of course, r square, r to the third, r to the fourth, and so on. So we will create shelves of these heights. So for example, if r is 1/2, then you will have a shelf of height 1, you will have a shelf of height 1/2, you will have a shelf of height 1/4, you will have a shelf of height 1/8, and so on and so on. So we pack and we put each rectangle or box, if you wish, each rectangle onto a shelf where it fits. I mean, for the height. But the next possible smaller shelf is too short. But so the next shorter shelf has a smaller height than the rectangle. So it's too small. Smaller height than the rectangle. So into the smallest possible shelf onto which it fits. Smaller height than the rectangle. Now inside the shelf, so inside the shelf we are just packing the rectangles next to each other. So the rectangles get packed next to each other. So onto the bottom of the shelf. And if there is not enough space on the shelf, for the box, for the next rectangle, then we just close that shelf forever. So it's kind of similar to the next fit algorithm actually. So that shelf forever, and open a new one with the same height. And that's basically the only thing which we do. Now let's just construct an example for this. Just run this on our previous example. So for example, if we just run the next fit shelf algorithm with parameter 1/2, because it's easier to compute with powers of 2, so not next fit shelf with a parameter of 1/2. How does it work? So the next fit shelf with a parameter of 1/2 on this input. First we are just constructing, well, shelves. In theory we could construct a shelf of height 1, a shelf of 1/2, height 1/2, and so on in advance, but we are opening those shelves only when some object gets actually placed onto them. So the first one, so the first box, has a height of 0.6. Now a shelf of height 1 is fine because this object fits onto a shelf of height 1, but it won't fit onto a shelf of 1/2. So that's why we are using a shelf of height 1 for this particular object. You can just visualize this like there was some actual shelf placed here, and we are just putting this object. So 0.4 is almost the half, and 0.6 is slightly larger than the half, so that's it. So it's 0.4 times 0.6. Now for the second one, for 0.3, it's enough to use a shelf of height 1/2. 0.5 if you wish. So we are now constructing a second shelf onto which we will pack our boxes. because 1 over 4, so I'm just trying to compute the powers of this number r, so it's in this case it's 1, 0.5, 0.25, 0.125 and so on, and amongst these guys 0.5 is the smallest one onto which this box still fits. So I'm just putting this here, it's just 0.3 times 0.3. Okay, so the drawing is not to scale. Okay, so then I have 0.5 times 0.4. Now that for that again a shelf of height 0.5 suffices. That's great. And also this box fits next to the one we already have on the shelf, and we still have a space of 0.2 left on the shelf, so it's 0.5 times 0.4. Okay, so we just put the second box there. Then we have the 0.1 times 0.7. Now 0.7 is again a height for which we should use a shelf of height 1 because 1/2 is too small, which means that we are just putting this guy there, 0.1, 0.7. Cool. And for the next one, 0.7, 0.1, it's enough just to open a shelf of height 1 over 8 because that's 0.125, which is already larger than 0.1. And of course the half of this quantity is too small, which means that we are just opening a shelf of height 1 over 8, and then we are just putting this 0.7 times 0.1 object there. So this is how it goes. And for example, just to see an actual closing, so if we, for example, at this point get an object of width 0.3 and height say 0.4, then 0.4 says that it should be packed here, but we already have a box of width 0.3 and a box of width 0.5, which makes it total 0.8, and 0.3 would make this total weight be larger than 1, which means that in this case we are just closing this box, this shelf, and we just open a new one with height 1/2, and we just put the 0.3 times 0.4 guy there in this case. So that's how it works. These shelves are closed forever. So essentially for any given height we are just running a next fit algorithm, and that's why it's called the next fit shelf. You just use shelves and apply the next fit algorithm for those. Now in this case the total height which we used is 1 plus 1/2 plus 1 over 8, and for this last one we were just using 0.4 instead of 1/2 because it will be the height of the total height of the box having the largest height on the topmost shelf. So it's just well, it's around 1.9, so it's 2.025 in this case. Of course it's larger than the optimum at this point. So this is how the next fit shelf algorithm operates. Of course, if you are just doing with this with say r equals 1/3, then you would just put this guy onto a shelf of height 1, this guy onto a shelf of 1 over 3 because so 0.33 is still larger, but this guy would use a shelf of height 1 because that's larger, and also this guy would use a shelf of height 1. Now this guy would use a shelf of height 1/9, because that's the power of 1/3, which still upper bounds, and then for this guy we should use a shelf of height 1. Okay, and in that case we would use, say, 1. Okay, this would fit, this would still fit, and this would still fit onto one single shelf. This we use another shelf, and for these two we would use 2 separate shelves, so it would cost 1 plus 1/3 plus 1/9, so far it's 1.44, and plus on the topmost shelf we would use a height of 0.4, so that would be something like 1.84 in that case. So for r equals it would be 1.84 for round, so r equals 1/3 would be better in this case than r equals 1/2, but it's basically pure luck, because, well, we had luck having these clusters. Now let's just compute. Let's compute, or let's upper bound the. So let's upper bound the asymptotic competitive ratio again of this algorithm. Asymptotic competitive ratio of this algorithm. So we are managing open shelves and closed shelves. So total height of open shelves. So we can have a shelf of height 1 being open, and we can have a shelf of height r, and we also can have a shelf of r squared and r⁴ and so on. But since r is smaller than 1, then so we can have only one open shelf for each height at any moment. So that's just 1/1 minus r. That's a well-known equality for summing geometric progressions. So for example, if r equals 1/2, then 1 plus 1/2 plus 1/4 plus 1/8 and so on is just symbol 2, which is of course 1/1 minus 1/2, which is just 1/1/2, which is just, again, yeah, cool. So, but this holds for any possible r between 0 and 1. Okay, so the total height of open shelves is this guy here, which is a constant. Similarly to the case of the analysis of the harmonic algorithm, we had k open bins, but the k was dependent only on the parameter but not on the input, which is this case, in the case here again. Now let's check. Let's check the situation with the closed shelves. For the closed shelves, so for a height, okay, so for a height, r to the h, the r to the h, we can have a shelf of height r to the h and another one r to the h. Okay, so suppose we have two of these guys. Now there are rectangles or boxes packed here, and we can have an empty space here, and they of course can have empty space on the upper part of the shelf, and we can have some other boxes on the second closed shelf of the same height, and of course we can have some empty space. But here this is smaller than this because we opened a new shelf, right? So that's why we opened this shelf, the second one, in the first place, because the next box to be put there was thicker than the space we have. So this means that the total width of boxes on these two shelves is more than one, because already these boxes plus this box have a total width larger than one, and also we have these other boxes passively. Now the total height, so the height of these boxes since we packed these boxes onto this shelf and not the smaller one, each of these guys have a height which is at least r to the h plus 1. Since if a box would be of height at most r to the h plus 1, we'll put this onto a smaller shelf, right? So that's why the total area actually used on these two shelves is at least 1, the width, times the height, the minimum height, so it's at least r to the h plus 1. And the total area of these two shelves is exactly 2 times r to the h. Yeah, so it's 1 times r to the h plus r to the h, so it's 2 r to the h, which means that the ratio is r to the h plus 1 divided by 2r, which times to the h, yeah. So at least this amount, which is r half part of the area, is used of their area is used. So for example, if r equals 1/2, then we are using r half, which is 1/4, or a quarter of the area is actually used on these shelves. So for example, if we have say 7 closed shelves, of height, of some height, say r to the h, and then again, similarly to the case when we analyze the next fit algorithm, we have one closed shelf and the second closed shelf and the third and the fourth. There might be other shelves, but we are just using these, so these should have the same height, of course, but we know that these two shelves actually use R12 percentage is used. And for these two guys, again, we have at least R12 which is used by boxes. And this is again, at least R12 is used. Now there might be, it might be the case that we have an odd number, just like this, because we have the 7. It might have an odd, but the height in this case is of course at most R to the H. At most, because if this is the topmost shelf, then it's a bit shorter. So this means that actually we can just partition those shelves which show the total height is just the sum of open shelves height plus the sum of the closed shelves height. And of course we already proved that this is the sum of the open shelves height is at most, yeah, this one here, 1 over 1 minus R. Okay, and we have that for all the possible closed shelves. Now for each height there might be one which is not paired, might be one unpaired, but the sum of those guys, again, for each height we have at most one closed shelf which is not paired with some other. So the total height of these guys is again at most 1 over 1 minus R. And the rest use at least R12 percentage of their area in total, because if this percentage is used for each pair of those shelves, then this percentage is used in the sum of their. So this means that of their area, which means that, so this part is, since optimum is at least the area of the boxes, and the area of the boxes, total area of the boxes is, well, is at least R12 of those shelves total area, but since the width is 1, we can just use the height here, which means that if I'm just dividing this guy by this guy, so those shelves height divided by the optimal cost will be at most So I just have to divide by the optimum, and to put this on the other way, I will just have to multiply the 1 by 2 over r, by 2 over r. Okay. Now this again means that we have a ratio of those shelves which is not exactly the algorithm's cost, but there is only a constant of 2 over 1 minus r, which can be the difference of the actual output of the algorithm and the paired closed shelves total height. So since this differs from the optimum, this differs from the output, of the next fit shelf R algorithm by at most 2 divided by 1 minus r. This means that the asymptotic ratio, competitive ratio of next fit shelf is at most 2 over r, because the constants will tend to contribute by 0 to the ratio algorithm divided by optimum if the algorithm's cost and the optimum cost both diverge to infinite. Then it doesn't really matter that we are just adding or subtracting a constant to the denominator. So this means that the asymptotic competitive ratio of the next fit shelf algorithm is at most 2 over r. So that's what we have for next fit shelf, and that was the last video about beam packings. And the last topic which we will cover is the topic of the K server problem. We will start it in the next video. Till then, bye bye.